All right. Well, hello, everyone. This is Michael Molina. I'm with the Oklahoma Transportation Library and the Southern Plains Transportation Center. We're happy to present our annual SPTC Thesis Award webinar. We've got a couple great award winners with us today. They are Melissa Escalante and Rodrigo Benitez. Melissa's going to present on her work entitled Assessing Delamination of Concrete Bridge Decks with Aging in Arid Regions Using Non-Destructive Methods, and Rodrigo is going to present on Developing Affordable Smart Solutions for Police Reporting. We're going to go with Melissa first, who will present for about 15 to 20 minutes, followed by Rodrigo, who's going to do the same. After that, we'll have some time for question and answer. So while they're presenting, I'd ask everyone to make sure they're on mute or you've muted yourselves until both of the presentations are finished. So after that, you can unmute yourselves and you can ask questions, or you can type in the chat box any questions and then we can read them off to them. So without further ado, I'll go ahead and start things off with Melissa. All right, Melissa, can you hear us?
Yes, can you hear me?
Yes. Are you able to share your screen with us? There should be a button, like a share button.
You can.
Okay, great. Yeah, we can see it.
Okay. So I'm going to start off my presentation today for the SPTC's 2019 Thesis Award Winner. I would like to thank the SPTC for this award. And I'm going to go ahead and start off by presenting the title of my work, which is Assessing Delamination of Concrete Bridge Decks with Aging in Arid Regions Using Non-Destructive Testing Methods. So I'm going to start off with a brief presentation outline. I'm going to start off with an introduction. I will proceed with the data collection, experimental investigation, data analysis, and I will finish with the summary and conclusions of the work. So non-destructive methods of infrastructure, it's basically an applied variety of analysis methods that evaluate infrastructure components without the typical destructive techniques. They have shown to be very reliable testing tools due to their efficiency and convenience, and because they can often provide infrastructure owners with potential tools for decision making. So for this work, the problem statement, it's basically what is known as delaminations. Delaminations within concrete bridge decks occur due to the water and salts that manage to penetrate the concrete to the location of the reinforcement, resulting in the corrosion of the reinforcing steel. At the same time, a fracture parallel to the steel. A fracture parallel to the surface of the concrete is often induced at the top of the reinforcement layer due to the corroded rebar. As we can see in this image, this typically shows how a corrosion is shown in a bridge at the location of the corroded reinforcement. And so the objective of this work was to expand knowledge and better understand the advantages and limitations of different destructive testing methods. And for this purpose, we use various tools such as the Portable Seismic Property Analyzer, which is also known as a PSPA, ultrasonic tomography, for which we use the MIRA, penetrating radar, and resistivity. So I'm going to start off by introducing each of the methods that were used for this work. So the first one is the Portable Seismic Property Analyzer, which is the PSPA. This instrument allows the determination of various properties and defects by monitoring the propagation of stress waves in the structure. Two types of propagation techniques are carried out with the PSPA, which are the ultrasonic surface waves and the impact echo. Depending on the type of evaluation being performed, the receiver-to-receiver spacing can be modified by the user. A receiver-to-receiver spacing of 4 inches will allow the structure to be evaluated up to a deep depth of 8 inches, while a receiver-to-receiver spacing of 6 inches will allow the evaluation up to a depth of 12 inches. So in the ultrasonic surface waves method, receiver 1 and receiver 2, which are shown in this image, are subjected to spectral analysis to develop a phase spectrum to calculate what is known as a dispersion curve, which is basically the variety of surface wave velocity with wavelength. Given that the modulus of elasticity of the material is a function of surface velocity, Poisson's ratio, and the mass density of the material, the elastic modulus with respect to depth can be calculated for the medium. With the IE method, basically what happens is that the near receiver's time record is used to determine the thickness of the medium or to obtain the depth to a defect inside the material. The impact analysis method consists of filtering the time record to minimize the surface wave energy and conduct what is known as a fast Fourier transform so that the return frequency can be calculated. With this equation, since the thickness is a function of compression wave velocity, the return frequency, and a shape factor alpha, which is usually 0.96 for concrete, the thickness of the medium can be estimated. This is the typical results that we get when we perform PISPA testing. And then next, I'm going to introduce what is known as the ultrasonic tomography, for which we use MIRA. This is a useful tool for detection of delamination and debonding, for measurement of thickness, and the determination of depth and location of reinforcement. This device basically consists of an array of dry point transducers arranged into 12 blocks, each block assessing 4 transducers. When the transducers impact the surface, they emit what is known as shear waves into the material, and they provide wavefront penetration that diagnose the structure up to a depth of 3 feet. The transducer array permits many pitch catch time-of-flight measurements to be made in a very short period of time, and the onboard computer in this device controls which of the blocks are acting as transducers and which are acting as receivers. Which ones act as transmitters and which ones act as receivers. After the structure is scanned, the 2D images that are collected can be are analyzed with appropriate software to reconstruct 3D images of the structure, providing the user with B, C, and D scans of the structure. With the MIRA, the depth of the medium can also be calculated given that the travel time from the initiation of the pulse to the arrival of the echo is measured. With the known shear wave velocity, once again, the depth of the member can be calculated. And this is a typical scan when there's delamination involved. We can see the shorter reflections due to the obstruction that the delamination or the defect causes. Next, I'm going to introduce what is known as the ground penetrating radar, which is the GPR. This is an NDT technique that is based on the principle of sending short pulses of low electromagnetic energy into the material. The GPR system basically measures the effect that the material has on the reflection of the transmitted pulse. From this device, layer boundaries can be reduced and various characteristics and assumptions can be formulated from the data. So basically what GPR does is it sends high frequency electromagnetic waves into the material. There's 2 properties of the material that impact the signal response, which are the electrical conductivity and the relative dielectrical permittivity of the material. This is a typical scan that's obtained when scanning the material with the concrete or the medium with GPR. We can see some reflections from shallow reinforcement, and then we have some other reflections from the bottom reinforcement layer, and then we can see the possible presence of delaminations in the scans. Next, I'm going to present the Winner probe, which is the tool that we use for resistivity to measure electrical resistivity in the concrete. The Winner probe basically works on the principle of applying a current between the outer electrodes, having the 2 inner electrodes measure the potential of the electric field. Since resistivity is a function of electrode separation, voltage, and current, resistivity can be calculated with this equation. When obtaining measurements for concrete, when we get low resistivity measurement, that indicates a high corrosive environment, and when we get high resistivity measurements, that indicates a low corrosive environment. And this is just basically the best way to place the probe when testing concrete, which is the furthest away from the reinforcement, to obtain better readings. So these methods were applied to a reinforced slab, emulating a bridge deck based on TechStat standards. Data was collected regularly with each device over 28-day span, and then it was monitored thereafter every 3 months. For this, the slab that we built was a 20 feet long by 8 feet wide by 8-inch thick concrete deck constructed at the University of Texas at El Paso. We had 2 regions. Region 1 represents a slab with 2 reinforcement layers using number 4 rebar, and then Region 2 was left unreinforced. So these are some of the cross sections of how the reinforcement ran along the longitudinal axis, and then how the reinforcement ran along the transverse direction. So here's a picture. Here's an image of how the delaminations that we used, the simulated delaminations that we used, were placed. So we basically had 8 artificially delaminated areas with various sizes and depths, using 3 millimeter thick cardboard material lined with plastic. The 4 larger delaminated areas have dimensions of 2 feet by 2 feet, while the smaller ones have delamination areas of 1 foot by 1 foot. And these are the shallow delaminated areas, and these are the deep delaminated areas. The vertical and horizontal spacing of the testing grid that was used was the one that we could see here, which is of 8 inches. This resulted in 29 testing lines along the transverse direction and 11 testing lines along the longitudinal direction. So we had an 8-inch spacing between each test point. And so there's some images of when we poured the slab. Here we could see the delaminations, and then here we have we can see some of the reinforcement, and then here we have some more delaminated areas, the simulated delaminated areas. So now I'm going to present the data analysis for the work. I'm going to start off with the ultrasonic surface waves. So I have data for day 1, 5, 7, 12, 15, 112, 200, and 260 post-pouring. We can see here that during the early days of the concrete specimen, the deep delaminated areas were detected by the ultrasonic surface wave method, but as we can see that as time progresses, the hardening of the concrete prohibits further propagation of the waves, and therefore the rapid attenuation of the surface waves, prohibiting us to see the deeper delaminations with time. We can also see that USW showed promising results in detecting the lower values of modulus during the earlier days. As we could see, we see them throughout the fresh concrete, and then as the concrete hardens, we can see these modulus values getting higher. And then, so for day 112, we wanted to see how the density of testing point affects the overall results. So for that day, we decided to test using an 8-inch spacing grid and then using a 16-inch spacing grid, and we could see that both results show promising results, though the 8-inch spacing grid does show more detail of the delaminated areas, and it captures a little bit, it aligns them a little bit better, but we can see that the number of test points isn't really critical to see the overall results, as the less dense grid presented promising results as well. It did show the areas of the shallow delaminated areas very well. And now I have a graph here of the average modulus through USW in non-delaminated areas with time. So we could see that as time progresses, the modulus value increases, and then it stays constant after about 28 days, which symbolizes the hardening of the concrete. And we could see here for both the reinforced and non-reinforced sections. Next, I have the impact echo results, which are also obtained by PISPA. The contours of the impact echo return frequency for the slab here at different times. We have day 1, day 5, day 7, 12, 15, 112, 200, and 260. A peak frequency of about 8 kilohertz dominates the response in the intact area, which basically corresponds to the return frequency of 8 inches, which is the thickness of the slab. We could see that at the flexural mode with a peak frequency of around 3 kilohertz is dominant for the shallow and delaminated areas. We could see that the impact echo showed promising results in detecting the shallow and deep delaminated areas with the dimensions of 2 feet by 2 feet. The smaller ones, however, as we could see, were not detected by the IE method at all stages, and this might be due to only having one frequency measurement at the location of each of these defects. A denser grid may therefore provide better detection of the smaller ones, of the smaller defected areas. And also, well, the smaller voids don't reflect as much energy, making them harder to detect. And here, once again, we have the data from day 112 showing the data with a testing grid of 16 inches and a more dense testing grid with an 8-inch spacing grid. And we could see a little more the defects on the denser grid, but once again, they both showed promising results, and it looks like less dense grid also shows to be efficient in detecting the defects. And here we have a graph of the average of the average frequency through IE in non-delaminated areas. We can see the increase in frequency. We can see the constant frequency with time, which pertains to the 8-inch slab concrete deck. So next, I'm going to present the ultrasonic tomography, which is basically with the mirror. These images represent the reflection amplitude of the multiple array paths of the shear wave transducer involved in mirror testing. This is at 4 inches, and then these are at 6 inches. The IntroView Concrete, which is the software that's used to analyze the mirror data, has a threshold slider option, which allows all boxes for which the signal amplitude is lower than the selected threshold to not be shown. So that's why we have these blank areas. When the slider option is left intact, we can see the scan reflection amplitude throughout, as shown in these images. So we see these lower reflection amplitudes here. We can see that the mirror showed very promising results in capturing all defects, including deep and shallow delaminated areas, as well as the reinforcement layers at each testing stage. We could see, however, that the first reinforcement layer is better contoured than the second reinforcement layer, and this is due to the shear wave amplitude reflection disruption that the first layer of reinforcement causes, yielding contours that show a disturbed alignment in the deeper reinforcement layers. However, we could see that the delaminated areas are clearly contoured for both deep and shallow defects throughout. And then next, I have the GPR, which is the ground penetrating radar data shown at different depths. We could see that for day 20 and day 22 post-pouring, we could see that they indicate major anomalies in the electromagnetic wave amplitude reflection at the location of the shallow defects. We can see, however, that during the later days, the reflections of the location of the defects are not as clearly shown, and this can be due to the hardening of the concrete. So as moisture is lost in the concrete, the dielectric constant of the concrete decreases, and so does its contact with plastic carbon material, causing less energy discrepancy between the two materials. So that's why we don't see this higher red reflections during the later days. We could see that GPR showed promising results in detecting the shallow defects. However, the deeper ones aren't as clearly shown, and this is due to the obstructions or interfaces at the shallower areas of the concrete specimen that cause the vast amount of the energy to be reflected back to the surface. We could see that the shallow layer of metal reinforcement presents a strong energy reflection from the electromagnetic waves at all stages of the concrete specimen. We could see that red high reflection amplitude aligned throughout. And then next, I have the contour maps, which show the propagation velocity of the electromagnetic waves with time. So we could see that as time progresses, the electromagnetic velocity increases. For day 20 and 22 post-spraying, we show a dominant electromagnetic velocity of 3 to 3.3 inches per nanosecond, while for the later days of the specimen, we show a higher distribution of electromagnetic wave velocity with values of more or less 3.5 to 4.0 inches per nanosecond. Mean present velocity represents a short travel time with aging, which basically is capturing efficiently the effect of concrete hardening. And here we're basically showing the average electromagnetic velocity through GPR in non-delaminated areas with time. Once again, we can see that increase, which once again represents the hardening of the concrete. Next, I'm going to present the electrical resistivity, which I previously mentioned. We used the Winner probe. We could see that, as expected, the resistivity increases with aging. It can be observed that overall the Winner probe is unsuccessful in detecting the delaminated areas and then this could be due to the aridness and hardening of the concrete over time. That increases its resistivity and therefore vanishes the probe's sensitivity to the high resistivity defects. However, during day 1, we could see that the probe did detect the plastic material of the shallow delaminated areas during the very early stages. We could see that at the location of the shallow defects and even some of the deeper ones, the resistivity values are higher, as shown here. And so this indicates the probe's ability to detect the defect's high resistivity carbon material as compared to the wetter concrete. For this one, we concluded that the process of delamination is on fresh poured concrete. It's not very common, so therefore the results from day 1 are just detecting the material's resistivity differences, and that's not very helpful. So we concluded that the Winner probe will show resistivity contrast when the concrete is actually exposed to humid climates, where these voids are filled with water and the corrosion process has actually processed in the concrete specimen. And here we basically show a graph of the average resistivity from Winner probe in non-delaminated areas. With time, we could see that the resistivity increased as expected. So just a summary of the work. So for this, we concluded that the USW method basically consistently detected the shallow delaminated areas, while the impact echo method detected larger delaminated areas, both deep and shallow. Ultrasonic tomography captured both deep and shallow delaminated areas, as well as the reinforcement throughout the concrete specimen live. For GPR, it could detect shallow delaminated areas efficiently during the very early stages. Deep delaminated areas were not as clearly noted. GPR detects shallower reinforcement layer thoroughly with aging, and then we also concluded that electromagnetic velocity increased with aging. For the Winner probe, it was unsuccessful in detecting delaminated areas with time. Once again, this is due to the aridness and hardening of the concrete that loses moisture, causing very high resistivity values and decreasing the ability of the probe to detect the difference between the concrete and the high resistivity voids. So the conclusions: all technologies seem to work efficiently in detecting certain defects. GPR is, however, limited in detecting delaminated areas due to the strong effect that the metal reinforcement has in the electromagnetic wave propagation. USW also presents limitation in detecting the deeper delaminated areas. And for the window probe, it can be further evaluated. Maybe if voids were filled with water, we might obtain better results, as the actual corrosion of reinforcing steel would be better simulated, and the areas of possible corrosion would be shown. And then additionally, just further research could be conducted on how test procedures can be modified given different cases of reinforcement in order to consistently identify defects beneath the reinforcement. And I would like to thank the Southern Plains Transportation Center, Dr. Musharraf Saman, Dr. Sahel Nassarian from the University of Texas at El Paso, and the Center for Transportation Infrastructure Systems, staff and students. Thank you.
All right, thank you so much, Melissa. That was awesome.
Thank you.
Let's go ahead and transition to Rodrigo. I'll go ahead and change your role to presenter, Rodrigo, and you should be able to share your screen. There should be a share screen button near the top.
Hello, I'm looking for the share.
Okay, yeah, it's coming through.
Okay.
All right, and again, make sure everybody's on mute, and then after Rodrigo, we could do question and answer for both Melissa and Rodrigo. So, all right.
Hello, everyone. My name is Rodrigo. I'm an OU graduate. Thanks to SPTC for giving me this award, and I will be happy to present my thesis to you. The name of my thesis is Developing Affordable Smart Solutions for Police Reporting. My original contributions on this thesis is that I developed a new cross-platform application for police electronic forms and reporting. This was developed together with another graduate OU student and CITS developer, Hisham Magluf. And this new application is a mobile app called Paris Plus, which is easy to use, is less expensive than comparing systems, and delivers high accuracy data. The problem is that many agencies, especially small ones, are still reporting crashes and speeding tickets using pen and paper. And you can imagine that this process is inefficient and takes a long time. And also data can be easily entered wrongly, which adds even more time to the process. However, we can fix this or improve it with technology because data accuracy and timeliness is critical for all levels. We have good technologies, but the problem is that they are expensive, and these smaller agencies cannot afford the solutions. So the focus of the thesis is to develop an affordable solution that could be more affordable to use with together with an inexpensive hardware. The topics I will cover on this presentation is just what are e-citation systems, the solutions that we have used in the state of Oklahoma over the past years, and the details of my implementation. So what are e-citations or electronic citation systems? These are just systems that allow officers to write citations digitally and submit them electronically. They help recapture revenue that is currently lost due to errors, and it reduces the contact time, which improves the officer's safety as well, because they can get back to their to their cars sooner. And it also reduces the number of mistakes that we see on the forms, because this software can provide front-end and back-end validation. Why is important to have this accurate data? The reason is that agencies managers need to use this data to make better decisions, and also making new policies requires a lot of critical thinking and data analysis, accurate data. So to be able to perform this analysis, we need to have uniform data, which is something that these e-citation systems can help with. And with the use of these uniform data, we can also improve the safety of the drivers. Some of the options or some of the previous solutions that the state has used include the handwritten forms together with OCR technology, optical character recognition technology, to try to digitalize the forms and store them, but you can imagine that didn't really go so well. And then the state moved to a system called Drugs, which is an initiative from Iowa. It's a good system, but it's not open source, and it's hard and expensive to customize. In order to be able to add a new feature to this software, you need to get approved by the other states that actually use this system, and then there is only one private company allowed to make changes to this software. So it takes a lot of time and money to actually customize the system to the needs of Oklahoma. So the CITS lab at OU was involved in trying to get drugs to meet all the requirements that Oklahoma needed. And that's how another system was born, which is called PERIS, which stands for Police Automated Reporting and Information Systems, developed by the CITS group, which is the drugs successor. And it came with basically unlimited customization and improvements that the state needed. And it also came with some compatibility with other software that the police officers use to track each other and communicate with each other, and ID scanners. So what is the problem right now? Is that we still have all these small agencies that cannot afford to run a system like this because they need to have expensive computers in their cars, and also an IT department to manage them. But the thing is that all these agencies or all these officers already have smartphones. So the focus of this is to try to take advantage of that. So that's why the solution that I implemented is, it's called PERIS Plus, which is a cross-platform application for Android and iOS. It was developed using Microsoft technology called Xamarin Forms, which allows to share 96% of the code between Android and iOS, and it's implemented using C#. Some of the most important features of the app that was developed is that it provides the officer with an option to just collect all the information about an incident or a ticket with just one click on a map. It comes with an ID parser that allows them to just scan an ID and parse all the information and put it on the form for them. And it also supports printing with inexpensive printers. This is a very key feature of the app because most of the printers that the officers currently use are so expensive. So we develop it in a way that it will work with very, very cheap printers. And we also have very unique and customized user controls to improve the experience of the application. The whole interface of the application itself was developed always keeping in mind that the officer has to do this on the road next to cars that are driving 70 miles per hour. So it's designed so that it will be super fast and easy to use, and we avoid directly typed fields at all costs. That means the officer only has to pick from drop-downs to make everything much faster. And wherever we can fill the information for him using something automated like the location tool, we do it to save him time. The authentication of the application is done using an API. So all the clients will make a request to an API, and this will generate a JWT, a JSON Web Token, to identify the users, and then all the future requests are made using this token. So this is a basic diagram of how this will work. The application will make a request with the username and password to the authentication server. It will be compared against the database. And then if the login is successful, it will return with a JSON Web Token, which the application will provide on any future request so that we can identify who is making the request. Another key feature of the app is these barcode scanning capabilities, which to reduce the time and developing costs, we use a third-party library that allows us to implement the barcoding with less effort. So we parse the information that is included on the driver license, and we use it to populate most of the form information, as you can see here on this animation. So all the form is empty, we just scan the ID, and then right away all the information is filled for them, except for some things that are not included on your driver license, like the race. Validation rules, this is a very key think of the application because we need to verify that the data is accurate. And this is what prevents the officer from submitting an incomplete form or a form that has a mistake. And so this is how we make sure that the officer is aware of what he's missing and that he can easily fill the whole form. So if you check here, we have these green checks to let them know, of course, that that field is complete, and these easy to see red crosses that let him know that they are missing something. As well, we also provide these global indicators so that the users can see where exactly is that they are missing information, and they can jump back and forward at any time to fill those fields. Another important feature is that we allow the officers to generate multiple violations with just one click. So usually when the officers are writing a citation by hand, they will write you a citation for the most, for the worst thing you did when you were driving. So that means if you were speeding, they would probably just give you a ticket for speeding and not for one for wearing your seatbelt, because they will have to write another ticket for that. But using this kind of application, they can just click another button, and then that will add immediately and your extra violation. And this helps the agencies to have more revenue as well. And this is what I was explaining before, that we support inexpensive thermal printers. And this allows us to keep the price way lower than the competitors. This is the printer that we choose to work with. It's like $70 or less dollar printer, and it does everything we need. We just had to write the drivers to work with this printer. This is the part I was mentioning before of how the officer can just look for a ticket, and just by clicking on it, they can add the ticket to your violations, and then just look for a second ticket, and as well just click on it, and that will give you 2 tickets, one for speeding and one for not wearing your seatbelt. This is all done together with an API written in Node.js, and this API is running through a server with mod security to improve the security of the server. Together with the application, the system also comes with a web citation manager tool, which allows the course to access all the generated citations, and so it's easy for the people to go and pay their citations. So they just come to this website, they can look for the violator's name, they can query the citation, they can print it for them, and they can pay it right away. This reduces the time, because otherwise they will have to mail these citations, and the process is longer. It reduces the time it takes for you to actually solve the problem. Some of the future work that we're needing is completing and testing the offline login, building some iOS dependencies, and doing beta testing and deploying the app using the app stores and their business-to-business services. So in conclusion, I was able to develop a low-cost solution for police electronics forms that leverage the smartphone technology available in every police vehicle already, today. We are able to perform data validation and quality assurance of the data. And Paris Plus dramatically decreases the time required for a contact, as well as it reduces the time required before the data is available for analysis. That's the end of my presentation. Thank you for your time.
All right, great. Thanks, Rodrigo. Okay, if everyone wants to unmute themselves now, you're free to ask questions. You can either do it in a chat box, or if you want to just say your question out loud. Now's the question and answer portion.
This is Dominique Pittenger. Melissa and Rodrigo, y'all did a great job on your presentations, and they both look like really great projects. So congratulations on that. I do have a question for Melissa. On those 4 methods, what's the difference if you were going to deploy one of those methods out in the field? What's the difference in time to deploy if you're using those for testing?
So for the most part, the P-spot is probably the most time-consuming method, and maybe the mirror and the winner probe might be, is if it's a dense grid. If it's a dense grid, if it's like a big slab, or if it's you have multiple test points, maybe the 3 of them would take time. Fastest one would be GPR, because you just basically move the structure, move your instrument above the structure, and you just scan it in the X and Y directions, and it's fairly fast, and it could do long distances in an acceptable amount of time. So the GPR would be probably the best in time-wise.
But it looked like GPR was probably not the best in results-wise, huh?
Yeah, it was probably not the best. The mirror, it's very fast in like testing a point, but if it's several of them, it's gonna take time. But yeah, if it has to be the fastest, then yeah, that would be the GPR.
Okay, thank you for that. And Rodrigo, have y'all deployed that application just yet, or have y'all done pilot studies?
We haven't yet. That's part of the future plan.
All right, thanks.
All right, any more questions? All right, if there aren't any more questions, I'd just like to give a big thanks to our presenters. Thanks for taking time out of your day and for giving such great presentations for everybody. We've been recording this, and once we have it finished, we'll save it and upload it and send it out to everybody. If you want to share it or listen to it again, we'll have that available for you and sent to your email addresses. So thanks again to our presenters, and thanks everybody for coming and listening in, and stay tuned for more webinars once we post them. So thanks everybody, appreciate it.
Thank you.
Thank you.